Hello, everyone, and welcome to another edition of my physics lectures online. This is chapter 6. This is lecture number 4, where we're going to be talking about springs. And I refer everyone in my class to page 10 of your note packet. So a few important notes on springs, sort of the conventions surrounding springs, what we call positive, what we call negative. They're a little bit different from what we've looked at so far, where you have a straight line and you can just sort of define a 0 point however you like. You can define a positive direction however you like. With springs, there are some fairly strict conventions. So the x position of x equals 0 is defined as the position where the spring is in its relaxed state. In other words, it's not either going sproing outwards or it's not being stretched beyond some sort of a neutral point. So that's what x equals 0 means. When we talk about displacement and force of a spring on the block, by convention, a force applied to the spring is considered a negative force if it is going to the left, and a positive force if it is going to the right. So a negative force is one that compresses it, and a positive force is one that extends it. Furthermore, in terms of displacement, a negative displacement, or negative x, is one where the spring is compressed, and a positive displacement is one where the spring gets extended. So again, negative x, negative f is going against the spring or pushing the spring inwards. Positive x, positive f is stretching the spring outwards. When work is done on the spring by an outside force, so if I were to take, some sort of, well, let me get the annotations bar up here. If I were to exert a push in that direction, from this outside force, so we'll call that FO, this force would be doing work on the spring. And by convention, if you have work that is displacing this block from the 0 position or further away from the 0 position, that is called positive work on the spring. So if this mass is going to the left or to the right from this 0 position, if it's kind of going outwards, you could say, in the spring, that is considered positive work. Whereas if this outside force is doing work that brings the mass back towards the center, back towards the 0 point, that is considered negative work. The exact opposite, of course, is what's going on when we're considering work done by the spring. So that is work done on the block by the spring. And it's very important to keep track of who's doing the work on what in these kinds of problems. In that case, when we're looking at work done by the spring, it is negative work if you are moving away from this 0 position, and positive work if you are moving back towards this 0 position. A way to think about this is it's fairly intuitive when you think about it. You have a spring, and if I compress the spring and I have a block at the end of this spring, and then I let the spring go sproing, let me do that a little bit slower, sproing, the spring is transferring its energy to the block and therefore doing positive work on the block. Similarly, if you are extended beyond the neutral position of the spring and you let this block go, this block is being accelerated by the spring, which means that it is having positive work done on it. So keep that in mind. Work done on the spring, it's positive work if you're displacing away from the 0 position, negative work if you're displacing towards the 0 position. However, when we're looking at work done by the spring, it's the exact opposite. So just keep that in mind for the rest of your life. The work done by a spring force is defined partially by Hooke's law. So if we're looking at spring force, to a good approximation for many springs, the force from a spring is proportional to the displacement of the free end, in other words, the end that's not tied to a wall or something like that, from its position when the spring is in its relaxed state. The spring force is given by F equals negative kx, where x is the displacement from 0 and k is the spring constant in newtons per meter. So k, again, is a constant. It's something that will vary based on how tightly coiled your particular spring is. And notice that this force is negative So it is opposing the direction of motion. And also note that this is the force that is coming from the spring acting on the block. So if you have something that's going in a positive direction, then the force from the spring is considered to be acting in a negative direction. So the minus sign indicates that the direction of the spring force is always opposite the direction of the displacement of the spring's free end. The constant K is called the spring constant or the force constant, and it's a measure of the stiffness of the spring. The work, W sub S, done by a spring when it moves from X initial to X final is given by this expression, where we have minus 1/2 Kx final squared plus 1/2 Kx initial squared. And again, this is work that is done by the spring. It is not work that is done on the spring, it is work done by the spring. And that simply comes from taking an integral of this force function over a particular distance bounded by the initial and final conditions. So if you do this integration, this is what you get. If we're looking at work that is done on the spring as opposed to work that is done by the spring, this is going to be opposite in sign. So the force in this case would be plus kx dx, and we would have 1/2 kx final squared minus 1/2 kx initial squared. That's when we're doing work on the spring as opposed to work being done by the spring. If you ever get confused, all you have to do is say, all right, plug in some value here in final and some value here in initial. And let's say that the final value of x is larger than the initial value. In this case, the work would be negative if you have x final being larger than x initial. And that makes sense because when we're looking at work done by the spring, the work done by the spring is negative if x final is greater than x initial, and vice versa. It's kind of a quick sanity check. Work, W sub S, is positive if the block ends up closer to the relaxed position than it was initially. And again, that is for work that is done by the spring on a mass. If the block attached to a spring is stationary before and after displacement, then the work done on it by the applied force displacing it is the negative of the work done on it by the spring force. So in other words, what this is saying is that the force applied is going to be opposite in sign to the force of the spring. So when we have force applied going in this direction, then force of the spring is going in that direction. Remember that forces are happening in pairs. Just something to keep in mind there. Right? So let's take a sample problem when we're looking at work done by a spring. We have here a spring, there's a rest position, and there has been a displacement of 2 centimeters or negative 2 centimeters, meaning that we have compressed the spring by 2 centimeters using a force of 80 newtons. If we slowly move the block so our force does 4.0 joules of work, what is the final displacement of the block? And it's also enjoining us to remember that there are 2 possible answers. Where would those 2 answers be coming from? Well, we could do work on this system either by compressing the spring further or by allowing the spring to return to its neutral position and then stretching it. The first thing you want to do whenever you're dealing with springs and you're not told the spring constant is to find the spring constant. And in this case, what we say is F is equal to negative kx, and the force in this case is 80 newtons. That's what we're told up here. I'll go ahead and draw that in. So we have a force of 80 newtons. We have a displacement of negative 2.0 centimeters. The reason that we write this as negative 0.02 meters is that K is by convention given in newtons per meter. And that's a very important thing to remember, considering that a lot of times the displacements you're looking at in springs will be given in centimeters. So remember to do that conversion. Remember to deal with displacements in meters. We can just simply plug and chug here, and we find that K is equal to 4,000 newtons over meters, right? Next thing we do is we pull up our handy-dandy expression for work, and this is W equals 1/2 kx final squared minus 1/2 kx initial squared. And we make the necessary substitutions. We say that x1, or x initial, is negative 2.0 centimeters. We know what K is because we found it, and we know that the work is 4.0 joules. We go ahead and make our substitutions. And then we have to remember that this is, it's possible to obtain this amount of work from either extension or compression. So that's where this plus or minus comes in. So we rearrange to get xf squared by itself. We do that rearrangement, we take a square root, and we remember that this plus or minus, when taking the square root, is important because we're looking at possibly extension or compression. And if you go ahead and solve this, you should wind up with the final position either being x equals 5 centimeters or x equals negative 5 centimeters. For my morning class, I'd like to apologize. I actually did this incorrectly in class. So please take a look at these notes and disregard what I told you way back when we were still holding lectures in person. All right. So looking at the next problem here, looking at the previous figure again, but assume it's a new spring, we gradually pull the block from x equals 0 to x equals positive 3 centimeters while it is stationary. And the figure below gives us the work that our force does on the block. So in this particular figure, this is work, and this is displacement. We then pull the block out to positive 5 centimeters and release it from rest. And we're wondering how much work does the spring do on the block when it moves from plus 5.0 centimeters to either of these positions, right? Again, first thing you want to do when you're dealing with a spring is to find K. And in this chart, we actually have a fairly convenient way of doing that. Each of these lines actually represents a tenth of a joule. So this is 0.2. And if you count them up, there are in fact 10 of them between 0 and 0.1. So if we look at this position, we know that a displacement of 1 centimeter is requiring 0.1 joules of work. So we go ahead and we say, all right, the work is equal to 1/2 kx squared. Our x initial in this case is 0, so we can go ahead and disregard that part of the expression. We know that the amount of work that had to be done was 0.1 joules, and then that's equal to the spring constant times 0.01 meters squared. This 0.01 is 1 centimeter in meters, and then we find that K is equal to 2,000 newtons per meter. So that's pretty straightforward. Then what we do is we take our expression for the work that is done on the spring, and we say that that's equal to 1/2 kx2, or x final, squared, minus 1/2 kx initial squared. And we go ahead and make our substitutions. It's asking us in this case asking us for the displacement either to plus 2.0 centimeters or minus 2.0 centimeters. It doesn't actually matter if we plug in positive 2 or negative 2 centimeters here because it's squared in either case, and that's going to get rid of the negative term. So we go ahead and plug in, and we find that the work that is done on the spring in this case is negative 2.1 joules. But that's not asking us for the work that's done on the spring. It's asking us for the work that is done by the spring. And we remember that the work done on the spring is equal in magnitude but opposite in sign to the work that is done by the spring. Again, remember that the force of the spring and the force external applied on the spring are opposite in sign but equal in magnitude. And that's what allows us to say that the work on the spring is equal to the negative of the work done by the spring. So we go ahead and we say that the work done by the spring is the negative of negative 2.1 joules, or 2.1 joules. If we look instead at the 5 centimeter case, we find that the work on the spring is equal to 1/2 times 2,000 newtons over meters times 0.05 meters squared minus 1/2 times 2,000 newtons over meters times 0.05 meters squared equals 0. And actually, one of these should be a negative. I forgot to write that in, but trust me, one of those is going to be a negative, and we find that it's 0 joules. So this is an important insight that we have into the behavior of springs. If you have a particular displacement from that relaxed position, if you start over here and you move it over here, so you go from it being compressed a particular distance to it being extended a particular distance, then the amount of work done is 0. You have to kind of consider the absolute value of the displacement, if you will, from that 0 position when you're trying to determine work. So again, very important insight, and keep that in your back pocket. Work depends on absolute value of displacement relative to 0. All right, so that concludes our discussion of springs. Next time, or in the next video, I will be discussing the concept of conservative and non-conservative forces. I will see you next time, and take care.